Hello, Christian.
Hello, Phil.
So you are working in the Accelerator this week?
Yep, we are trying to prepare new silicon dioxide samples where we use the swift heavy ion irradiation which is created here to create damage in the material.
Right, so silicon dioxide is sand? Glass?
Essentially glass.
Yeah. And you're basically just breaking glass?
Yeah, that's actually a quite good description. Yeah, we're using the ion irradiation essentially as a nano drill, so we create damage in the material.
You're just accelerating particles? What sort of particles?
In this case, it's at the moment silver, and tomorrow we're switching to gold.
Okay,
gold
so you just shoot basically bullets of silver or gold.
Yeah, we throw
at
gold
glass,
atoms on glass, yeah.
And that kind of creates a drill hole kind of thing, is that what you're saying?
It creates first damage, so it doesn't drill immediately, but the damage we can use to actually use an etchant, some HIAF, to etch through the sample. And
so what is the damage?
The damage is essentially a modified density of the material, so we create misplaced atoms and breaking up the bonds in the glass, so it becomes more easy to be dissolved in an etchant.
Right, okay.
And then we can use the etchant to etch away the modified material.
So etching is just dissolving it with an acid or something?
Yeah.
What do you use?
HIAF, hydrofluoric
acid. That's very
so
strong.
One of the most nastiest materials we have here. And this allows us to create very, very long, so micrometer long etch tracks, but at the same time they are only 10, 15 nanometer in diameter. And that's really, really interesting.
So a tiny little hole that passes right through a glass. It's not a crystal, is it?
It's
a piece
amorphous.
Of glass.
It's
amorphous.
glass.
Yeah, okay. Once you have the hole, what comes then?
Then we hope to understand, first of all, the etching process and the preparation better. And once we know how to really tune the size exactly, we are able to hopefully use it for DNA sequencing and things like that. So because they're this extremely small, we can measure electrically how a molecule passes through. And different size molecules like DNA give you a slightly different ripple in the electrical measurements. Therefore, it is an idea of third generation DNA sequencing. But the problem at the moment is really the etching conditions and how the irradiation conditions influence these tracks.
So you've got to make the perfect little hole, and then you try and feed a whole string of DNA through it, kind of thing, and see how that affects the electrical signal within the silicon dioxide.
Yep.
Okay, that's cool.
So
that's very cool.
If everything works, it will be a very easy to produce silicon technology compatible, so normal computer technology compatible system, which can create very cheap and easy to use sequencer for molecules, not only DNA, also other chemicals. It can be interesting as a sensor. Another interesting application would be that if we make them even smaller, that we can retain salt and do water splitting, so water desalination, things like that. The amount of application is actually quite large, but the very fundamental thing we are interested in is how do we get there? How do we produce nanomembranes in a reliable way and understand how it works? Because ultrafiltration systems you can buy off the shelf today, which are also ion irradiation created, but the producers claim you can use the recipe and you will never ever get their results because the understanding of the very fundamental process of the ion track formation and the following etching is still something we have to understand better.
Is it tricky with glass because it's amorphous, so it doesn't have a regular structure, so it's hard to tell what it's going to encounter and therefore what the damage is?
No, it's more like the whole process itself. There's little to no understanding of a lot of steps in between. We have a good idea nowadays, thanks to molecular dynamic simulations, what these ions do in the material. But still, these simulations has to be backed up with experimental results, and then it's also still a question what kind of breaking bonds and what makes it actually susceptible to the dissolvent, to etching, which you asked earlier. This is still not 100% understood actually. What actually makes them better dissolvable? Because it could be also that the exact opposite actually happens. That due to higher density, it dissolves slower, but we don't observe this. So it's still something we have to dig deeper.
So what do you know about the process as it passes through? It breaks a few bonds. Is that from momentum transfer, or is it?
It is not a momentum transfer. It's actually an energy transfer through the electron system. So the swift heavy ions we are shooting here with 185 mega electron volt on the samples, which is quite a lot. It's about 10% of the speed of light.
Wow. Okay.
So not that slow. And in this case, it is actually very fascinating that it changes. Low energy ions collide with the atoms, and you play essentially billiard. While with the high energy ions we're using here, they do not interact really with the atoms. They release their energy into the electrons, and they heat up the material. So we create a very tiny little area, which becomes really hot and almost molten. Or sometimes even molten actually. And this creates the damage in the material.
So this tiny track of liquid, which then solidifies again, and then the etchant can attack that preferentially somehow. Wow, fascinating stuff.
And why exactly, or what exactly is attacked faster, we still have to look into more details, and that's part of the experiments we're doing at the moment.
Okay, I'll let you get on with them. Thank you.
Thank you very much.